All right, so now we're going to start looking at phases of matter and the gases. We've looked at solids, we looked at liquids. Now we're going to start looking at gases. So the first part of this, we're going to look at KMT again, the kinetic molecular theory, Boyle's law, Charles' law, the combined gas law, and the ideal gas law. All right, just to rehash, elemental states are at 25 degrees Celsius, okay? There are 11 gaseous elements. 5 of them are diatomic. And then you have our lovely 2, mercury and bromine, that are liquid. All right. And so just a rehash of the molecular theory, the volume of a gas particle themselves is negligible, like means it doesn't, like they don't actually have volume compared to the volume of the container that they occupy, which means gas particles are so small, while the distances between each one is like so big, so far. All right. Gas particles, they move rapidly in random straight lines, and they can bounce off stuff. And remember, when they collide with walls, that causes pressure. When molecules collide with walls, it causes pressure. The average kinetic energy, the temperature, of a gas particle is directly proportional to the Kelvin temperature. So the movement is proportional to Kelvin. Remember, 0 Kelvin, which we can't reach on Earth because the Earth is, spinning. You can't stop the movement on Earth because of that. Like, it's spinning. You can't stop it. Number 4, collisions of gas particles with each other and the walls of containers are elastic and cause pressure. The gas molecules are assumed to have 0 attractive forces to one another, yet they don't want to be near each other. Some of these do not always hold true, but we'll discuss that later. All right, so here's some gas laws, or the gas law. And gases are defined by 4 measurements. 4 that we're going to look at. Actually, it's more we're going to look at the first 3 as opposed to the last one, but I'm going to throw that last one in just so that you know and have that in your thought process. So pressure, volume, temperature, 3 things that we're really going to look at, and then the amount. These quantities are mathematically related, whether they're direct or indirect. And the relationships between volume, pressure, temperature, and moles, all of those are referred to as the gas laws. Okay, so first you have this dude named Robert Boyle. So you have this dude named Robert Boyle. What he did, what he studied, was the relationship between pressure and volume of a gas when the temperature and the amount were held constant. So he found that on a sample of gas, it decreases the amount of volume at constant pressure. So if I kept the temperature and the same amount of moles in there the same, and I start pushing down on this, I'm going to find that even though I have the same amount of the stuff in there, it's the same pressure, I'm going to have less space that it takes up because you're getting rid of some of the space. Okay, you see that as it gets pushed down? Because of that, we find that volume of gas is inversely proportional to its pressure. In other words, it is indirect, has an indirect relationship. As one goes up, the other one must go down, and vice versa. So it leaves you with this formula. P1V1 equals P2V2. And in this case, P1V1 equals P2V2, which equals P3V3, which all equals 1 liter per ATM. That's pressure and volume. 1 liter, 1 ATM. Okay? All right. So doubling the pressure reduces the volume to half its original value. That was just real quick, and I did notice that. So you've got P1 V1 equals P2 V2 again. So looking at this, if my pressure, say my pressure is up here at 4, or sorry, 2, and I double my pressure, or sorry, okay, so if we're starting here, 1 right here, and my volume's 4. If I double the pressure, I go up to 2 atm, you'll notice volume is halved. So it's now down to 2 to 2. Now, say if I go from 1 to 4, look at this. At 4, it's roughly 1. It's a quarter of it. All right? So then you have Jacques Charles. Charles studied the relationship between temperature and volume when we hold pressure and amount constant. So when you heat a sample of gas, its volume increases. Likewise, if you decrease the temperature, if you take some of that temperature away, it will decrease the volume. So this one is proportional, or directly proportional to the absolute temperature. So it means it follows along. As one goes up, the other one goes up. As one goes down, the other one goes down. All right? So looking at this is what you see. It is directly related. So this is going to be V over T. So V1 T over T1 equals V2 over T2. This is Charles' law. Okay? So on a Kelvin temperature versus volume graph, the volume of a gas extrapolates to 0. Because remember, we can't get to 0, so we're trying to make an educated guess based on all of the measurements that we can actually get to. All right, so this is showing you what I was talking about with Charles. So this is Charles' law. As you, in this case, decrease the temperature, you're going to decrease the space that the gas takes up. And in this case, it's in a balloon, so the balloon is going to shrivel. So if you've ever been outside with a balloon that you're bringing to a party, like a helium balloon, and it's near winter and it's cold outside compared to where you were just in, you'll notice that your balloon won't be as high up in the sky or won't be floating as much. It'll be like it'll sink a little bit, right? And this is what this is. I wanted to show you guys just a little bit. This person is putting a fully blown up balloon into some liquid nitrogen and then setting it aside. It shrinks, but then as soon as you let it alone, it starts to heat back up. When it heats back up, it re-inflates the balloon. Okay, so then we have Avogadro. Just to let you know, don't worry too much about this. I'm not really going to go into much, but he really was looking at volume and the amount. So we're not going to look at amount too much. So I'm just going to let you know that he found that volume and the amount of moles, they're directly related. So as the volume goes up, the number of moles can go up. As the volume goes down, the number of moles can go down, as long as you keep pressure and temperature constant. Okay, so what can we do? We can combine all of those lovely laws together, Boyle's, Charles, and Avogadro's, and we come up with this lovely thing. P1 V1 over N1 T1 equals P2 V2 over N2 T2. Now, like I said, Avogadro's, we are not going to deal with that too much for chemistry right now. So you're just going to get rid of that N. And if you look at table T in the back, you will find that this is called the combined gas law. All right. And for the ideal gas law, so anything that is held constant can be removed from the equation. So if pressure and the amount are unchanged, they will cancel out. The equation reduces to Charles' law. Now, if, say, the amount and temperature canceled out, you're going to be left with Boyle's law. Okay? So then you have this thing called the ideal gas law. This is PV equals nRT. And this R is, if I was to calculate this out, at a normal STP, 1 ATM times 22.4 liters. Remember that. 1 mole is worth 22.4 liters. And again, this is over 1 mole at 273 Kelvin. All right, so if I actually calculate this out, I get 0.08206 liters ATM per mole Kelvin. Changing any of these measures for any gas sample will yield the same volume or value. So again, ideal gas law, PV over NT equals R, or PV equals nRT, where you have this. We're not really going to look at this again because we're going to kind of look more so at the combined gas law. All right, so just to let you know, when the ideal gas law is used, is when conditions of the system are not changed. All right, so real quick, we're going to do a couple exercises where we're, if you have to, convert temperatures to Kelvin. Are there any changing conditions? If there are changing conditions, use the combined gas law. Remove all constants. If it's not said in the equation, you can remove that as a constant. If, say, it says it's the same, whatever property is the same, if you've got the same 2 pressures, you can cancel those out. If you have the same 2 temperatures, you can cancel those out. For the combined gas law calculations, any unit of pressure and volume can be used, but the units must remain the same throughout the calculations. For instance, when using pressure, if you have ATM on one side, you have to keep ATM on the other side. If you have volume in liters on one side, you have to have volumes of liter on the other side. You cannot mix the two. For each of the following, tell me what gas law is illustrated. So looking at this, we've got sulfur dioxide, central to the formation of acid rain, is found in the exhaust of automobiles and power plants. If a 1.5 liter sample of sulfur dioxide exerts pressure of 5,600 pascals, what will the volume of the gas be at a pressure of 16.8 kilopascals? So looking at this, we can assume that because they don't mention temperature and they don't mention the amount, like the moles, we can cancel those out. When we do that, we got to plug in the numbers we have, but the pressures don't match up. So we know that a kilo is 1,000 times more than a base unit. Our base unit is pascals. So this is 1,000 of these equals a kilopascal. So just divide that by 1,000 and you'll get 5.6 kilopascals. So you have your pressures the same. When you do that, you can plug all these numbers in and you're left with 5.56 kPa times 1.53 liters equals 16.8 kilopascals times V2. Now, as discussed in class, what you can do is you can multiply these two together and then divide by this to get this answer. Okay, and this is Boyle's law because it's P1V1 equals P2V2. All right, next one. An 11.2 liter gas sample has 1.5 ATM, is heated from 100 Kelvin to 250 Kelvin, while its pressure is changed to 2 ATM. What is the final volume? So we don't see anything about the amount, so we're going to cross that out and just plug in all the numbers. When I plug in the numbers, one of the things we talked about in class, you could either multiply this, divide by that, times by this, and then divide by that. Right here, like just going through and doing it the algebraic way. You can also do the, I think it's called the butterfly method, where you multiply all 3 of these, multiply these, and then just divide what you have over here to get V2 by itself. When you do this, you should end up with 21 liters. This is the combined gas law. All right, so what is the volume of 2 moles? We are not going to do this one because it deals with moles. All right, let's see. This sample of gas at 15 degrees Celsius, 1 atm, has a volume of 2.58 liters. What volume will the gas occupy at 38 degrees Celsius? Well, look at this. 1 atm and 1 atm, pressure's gone. Get rid of that. And amount is gone. So we have V2 over T2, and that is Charles' law. When you calculate it out, you should get 2.79 liters. All right, and this last one we are not going to do. I will leave it here so you can see what it is, but we're not going to do this one. Don't forget to do the green sheets. Please delete 10, 11, 12, and 13. You do not need to do those. If you have any questions, please feel free to ask, and I hope you guys have a great day.